Hey guys, today we're going to look at elastic collisions in two dimensions. So the last video we looked at was inelastic collisions, collisions that hit each other and then stick together. These collisions hit each other and bounce off. So a great example for this is a set of billiard balls. So we've already learned that momentum is conserved when two objects collide. And because momentum is a vector quantity, it has to be true for each direction. In an elastic collision, the two objects bounce off of each other and travel in the opposite direction. So here's a simplified version of that example. We have a first ball that has a mass and a velocity, a second ball that has a mass and velocity. Once they collide, one ball travels in one direction and the next travels in the opposite direction. For all of these examples, we have two separate momentums before and after the collision because of the fact that they never stick together and they never travel together. But we are going to look at the x direction and the y direction at separate times. So on the next slide, I'm going to introduce some equations that are going to be useful when we do that. Now, this is a simplified version. Technically, in order to have these bounce apart and travel in a different direction, this first billiard ball should be coming in at a slight angle to hit the second one, or maybe hitting it right here at the very, very top, or on the side. The issue is when we do that, we add calculations in to an already kind of complex math problem. So for right now, we are assuming that this is x direction only. In addition, this second ball is always going to start with a velocity of 0. Just to make our lives a little bit easier for now. Billiard ball number 1 moves in the x direction only. Billiard ball number 2 always starts from a velocity of 0. Motion in the x and the y dimensions must be treated independently, just like they have in the past. The first bullet point is kind of a mouthful. The initial momentum in the x direction is equal to the sum of the x components of the final momentum for each object. So essentially, the initial momentum of the first billiard ball is equal to the x components of both balls after the collision. The initial momentum in the y direction is 0, therefore the final momentums for each object must cancel each other out. If one is positive 2, the other one has to be negative 2. So we're going to use some equations to get us there. So in the x direction, we have the initial momentum of the first object equals the final momentum in the x direction and the final momentum in the x direction of the first and second objects added up. Now, I don't ever tell you momentum, but I do tell you mass and velocity. So we're going to take m1 vi1, and then we have the final momentum, but the x direction only. So I'm going to use m1 vf1, but then I have to add cosine theta, because that first billiard ball, when it bounces off and goes in the upwards direction, I only want this component of its momentum. That's why I'm going to be using cosine theta. The second billiard ball is the same way. We want m2 vf2 and cosine theta 2. So it's a long equation. It's kind of an ugly equation, but it's a really easy equation to use because every problem gives you all of this information. In the y direction, we are now looking for this vector. And notice, the y direction doesn't have any initial components. They are only final components. So mass 1, final velocity 1, and since it's the y direction, we're using sine theta, equals mass 2, final velocity 2, sine theta 2. So every letter has at least one indicator. A number to tell me which object we're looking at, and a letter to tell me if it's initial or final. Okay? Now, on this slide, in yellow, I'm going to write something that's really important. If you are solving for an initial velocity, you must use the x direction. because there is no initial velocity in the y direction in our equation. So we can't solve for it because it's not even there. Alright, so here's our first sample problem. A student is playing pool and hits the cue ball with a mass of 0.17 kilograms into a stationary billiard ball of equal mass. The cue ball was originally traveling with a speed of 2.45 meters per second, and after the collision travels above the original path at 35 degrees with a speed of 1.2 meters per second. If the second billiard ball travels at an angle of 25 degrees below the path, what is the final speed? So first thing I'm going to do is draw a picture. Ball number 1, ball number 2. Ball number 1 goes above the path at 35 degrees. Ball number 2 goes below the path at 25 degrees. So now I'm going to list my knowns and unknowns. M1, VI1, M2, VI2, VF1, Theta1, VF2, and Theta2. So the first mass is 0.17. The second mass is 0.17. The first velocity is 2.54. The second is 0. The first final velocity is 1.2 at 35 degrees. And the second final velocity is our question mark at 25 degrees. So I told you that I'd show you one of each example. Since we are solving for a final velocity, for this example, I'm going to use the y direction. So I'm going to use my equation that sets the final momentum of object 1 in the y direction equal to the final momentum of object 2 in the y direction. In order to do that, I need m1 vf1 times sine theta 1 equals m2 vf2 times sine theta 2. So m1 is 0.17, vf1 is 1.2, sine 35. M2 is 0.17, we don't know vf2, but I know sine 25. If I multiply all of this first stuff together, I have a value of 0.117. If I combine 0.17 and sine 25, I have 0.072 VF2. Now in order to separate this out to get VF2 by itself, I'm dividing both sides by 0.072, and VF2 is 1.6 meters per second. So notice, since we were solving for a final velocity, one of the things in the final direction, I could use the y momentums in order to simplify and do a little bit less math. That's why I showed you this way of solving it. If you wanted, you could have used the x direction and done m1 vi1 equals m1 vf cosine theta 1 plus m2 vf2 cosine theta 2, and you still would have solved for this unknown variable. It's just a bigger equation. Now in the next problem, we're going to have to use that equation. A student is playing pool and hits the cue ball, mass of 0.17 kilograms, into a stationary billiard ball, mass of 0.15. If the cue ball was originally traveling in a horizontal line, and after the collision, it travels above the path at 25 degrees with a speed of 1.7. If the second billiard ball travels at an angle 30 degrees below the path with a speed of 1.5, what is the initial speed of the cue ball? Step 1, draw a picture. Ball 1 traveling this way. Ball 2 stationary. Ball 1 goes above the horizontal. Ball 2 goes below the horizontal. List your knowns and unknowns. M1, VI1, M2, VI2, VF1 and theta 1, VF2 and theta 2. So this time our masses are different, and everyone always asks, does it matter which number I give to which object? It doesn't, as long as you keep their information together. So you need to know that the 0.17 kilogram ball is the one that's traveling 25 above at 1.7. But as long as you keep the information together, it doesn't matter which one you make, ball 1 or ball 2. The initial velocity of ball 1 is the number that we don't have, and it's asking us to solve for. Initial velocity of ball 2 is 0. Final velocity of ball 1 is 1.7 at 25 degrees. Final velocity of ball 2 is 1.5 at 30 degrees. So since we're solving for the initial velocity, we have to use the momentum in the x direction, because that is the only one that has the initial velocity in the equation. So m1 vi1 equals m1 vf1 cosine theta, because x direction is the direction we care about, plus m2 vf2 cosine theta 2. Now plug in your numbers. 0.17 vi1 is the number I don't know. 0.17 times 1.7 times cosine 25 plus 0.15 times 1.5 times cosine 30. So now I'm going to combine our numerical values. 0.17 times 1.7 times cosine 25 is 0.262. 0.15 times 1.5 times cosine 30 is 0.195. Add those two values up, and 0.17 vi1 equals 0.457. Now, in order to get vi1 by itself, I need to divide out that 0.17, and vi1 is 2.69 meters per second. So in order for those two billiard balls to bounce off at the angles and the speeds that they did, the cue ball had to initially be traveling 2.69 meters per second. So in class tomorrow, we're going to look at solving for unknown variables using different scenarios of these problems. You are going to have only elastic problems where they're bouncing apart for the beginning, but eventually I'm going to start mixing the problems up, so you're actually going to be seeing some elastic and some inelastic on the same worksheet. So I'll see you tomorrow so we can start practicing.